my name is Alicia Howell, and my first paper is Cognitive State Monitoring and Design of Adaptive Instruction in Digital Environments. Lessons learned from cognitive workload assessment using a passive brain-computer interface approach. Long title. So just some definitions before we get too far into this, is that working memory and working memory load are two different things. So the working memory is the memory that is stored and needs focused attention for a short period. So this is when you're doing math problems or reading through text and you have to remember what you just read or what the equation is that you were just looking at to continue doing the math. That's working memory. And working memory load is the amount of memory being used at any given point. People also have what's called a working memory capacity, which is the total amount of working memory an individual has. Theoretically, you cannot surpass your working memory capacity. So if your working memory load gets up to capacity, then you're at high working memory load. Or past some certain threshold, you'd be considered high working memory load. Then there's also low working memory load. So that's something that's not very intensive and it's quite easy for you to process. And then two other things are the theta and alpha activity, which these are two of the 5 data streams in an EEG. And these are the two streams that working memory load is commonly detected in, according to my first paper. So the problem that these researchers are wanting to solve is to optimize a learner's experience using a BCI through measuring working memory load. So what they're essentially wanting to do is that for students who are learning something, they would like to use a BCI application that customizes the learning experience based on their working memory load. So if something's too easy, they start increasing the task difficulty, and if something's too hard, they decrease the task difficulty. However, previous experiments could not differentiate levels of working memory load without other variables. So it was very difficult for them to understand what was causing the difference in the data, if it was the actual working memory load, or if it was due to things like motor confounds. So low working memory load tasks would use less motor movements, such as mouse clicking or keyboard typing, than high working memory load. These would use more mouse clicking or more typing. Then also the stimuli are quite different for low working memory load and high working memory load. For low working memory load, the visual stimuli were usually pretty simple. It wasn't anything too complex or intense, so there weren't as many places for your eye to move and look at. Whereas for high working memory load, not only was there more complex visual stimuli, there's also auditory stimuli to create more things that the brain had to perceive at once, which then adds a different layer of activity in the brain that their machine learning was picking up in the classifiers. So these are some of the issues that previous experiments have come into when trying to judge working memory load, especially with things like EEG, where it's so sensitive to motion artifacts and other types of noise in the data, it can be very problematic. So this group went through 3 different processes. One, where there were 2 studies, and then 1 discussion section that outlined things that they learned from the first study and other literature that they used to improve the second study. So this was a rather longish paper, so I'm kind of summarizing each of these 3 sections of what their main takeaways were instead of doing an in-depth analysis into the entire thing, because that would take too long probably. So study 1 takeaways is that they had no motor confounds in the task. Therefore, their low working memory load and high working memory load had similar designs. This is because they hypothesized that a lot of the previous experiments, the classifiers used in machine learning, weren't actually classifying high and low working memory load. They were classifying the amount of motor movement involved in the two tasks. So despite their original hypothesis that the theta and alpha streams would be the most important ones, they saw no difference in theta values over time between low working memory load and high working memory load. This could be due to the motor confounds, is that perhaps in other tasks where the theta stream was recognized as one of the ones that changed the most and had the most prevalence to understanding working memory load, it was actually because of the motor confounds. So that means that it wasn't the actual brain activity for how intense the brain was working, it was just movement that was involved. In this study, the average classification accuracy on 10 learners was 76%. However, they did mention that if they brought 3 of those learners out of the data analysis, then they could reach an accuracy at 80% or more. I'm hesitant to trust that type of analysis because you're essentially taking data and be like, this data doesn't look good because it's bringing our average down, so let's remove it. And there's not actually that much of a difference between 76% and 80%. It's a 4% difference. And because their in is already so small, I wouldn't remove any data just to have a higher classification accuracy. Maybe if they had like 25 to 30 participants, and if they removed 3 of them, then that would bring their classification accuracy up. Then that would be a time where it'd almost be warranted to do that type of almost cherry picking in the data. But I don't think this is an instance where that should really impact the data that much and how they're presenting the data. So that's one of the problems that I had with this paper. And then they also noticed that the differences in high and low working memory load could be due to the perceptual differences in their stimuli. So they acknowledged that they were not able to remove the perceptual stimuli confound that they mentioned in previous tasks. Granted, they only had visual stimuli in their task, but that doesn't mean that there wasn't any perceptual confound. So instead of having both visual and audio, it was just visual, but the complexity was significantly different, that they think that might be a confound. So then in the review section, they go through explanations of the various things that can cause problems or that need to be noted to design an experiment based on working memory load. So one of the things is that learning tasks are not easily randomized due to their nature. What this means is that if you have a class that teaches algebra, something like x equals 5 plus 2y, that's pretty easy to solve. Most people can probably do that in their brain at this point, like without any paper. But then if you start going into quadratic equations, that might get more difficult to try and solve. But you can't do quadratic equation solving without doing the simple algebra first. So you can't randomize it by putting the quadratic equations first and not teaching the simple algebraic equations and putting those at the end. That would skew the complexity of that low working memory load task. So then it'd be even lower working memory load, which is not the goal of the experiment. And the high one would probably be too complex for them to even process or attempt to go through. So that's one of the problems with trying to do working memory load tasks. The other is that researchers should use the participants' subjective rating of working memory load as classifiers instead of objective ratings. So when you design an experiment, you have in mind what should be the high working memory load and what should be the low working memory load. But if you have participants who are reporting low working memory load tasks as high working memory load, you should use that as a classifier instead, because that means that it's more accurate to their perception of how difficult the task is instead of just throwing a generic blanket over everyone's data. And then, as we've talked about mostly so far, avoid confounding variables such as perceptual and motor confounds. These act as ways to train the classifiers but are not purely related to working memory load. Something that was discussed at the very beginning of the course is that, especially with EEG data, there's a lot of discussion whether something is truly brain-computer interaction, if it's just picking up like eye tracking essentially, or eye movements, because you can detect that in brain data, but it's not the same thing as detecting the intention of what the brain data is doing. It's just kind of a side effect that you could detect without brain data. So they're saying that if you avoid perceptual and motor confounds, then you will have something that's more purely brain data that cannot be detected with other physiological measurements. And then they also say to use a variety of working memory load tasks for training purposes, but do not use significantly different visual spatial tasks. So what this comes down to is that there should be a mixture of words, numbers, math, a variety of different things that induce working memory load, but they should all be within the same visual spatial area. So it should be small, compact, and in the center of the screen so that there's not a lot of eye movement going in different directions. The participants can just focus in one place and perceive everything for the same amount of time. So then you negate a lot of other variables that could be causing the differences in the data so that your classifiers aren't picking up data that isn't related to just the brain activity, which is what they're trying to pinpoint everything down to right now. And then, despite all of that, despite trying to make this really controlled task, they also acknowledge that psychological tasks used to train the identification may not be to the same caliber that realistic learning environments are. So you need to do a cross-task classification to equalize the training and testing data sets. What this comes down to is that if you're using a predefined psychological experiment, it is going to vary significantly from what would happen in the brain in a real learning environment. One, you would usually have those perceptual motor confounds in a real learning environment, but what you're wanting to do is train it on this like essentially pure brain data. That's not the best term for it, but it's the best one I'm coming up with right now, and use that to test on these realistic learning environments, and then also change the data a bit so that it can not change the data, equalize the data so that it's at the same intensity as the real learning environments. So that brings us to the second study. They built off of study 1. They used essentially the same task design or like methodology design, but they switched the tasks a bit so that it could take into account the modifications from the 5 points that we just discussed. Their classification accuracy didn't really change that much. It's 73% now instead of 76%, which is pretty similar to study 1's accuracy. And their classification results were only significant for 68% of the classifiers. So they had 32 different classifiers, and only 22 of them ended up having significance in being able to identify high working memory load and low working memory load. So what this tells us is that despite changing the task to be more centralized to these points that they discussed, it didn't really change their results all too much. I didn't go into an in-depth analysis of how the actual data and data streams ended up looking like. That's another thing, is that this paper did not really have any figures or representation of the data, which was kind of not great because then you couldn't visually look at what was happening and make those correlations. So yeah, there's not too much of a difference between the results in study 1 and study 2 despite the modifications. So some other comments that I had is that it felt really wonky having that explanation section between study 1 and study 2, which seemed more like a literature review than comments on their own results, which is usually what the paper's for. I'm not sure if this is common in papers, and I just haven't come across it before, when you're doing multiple studies and you kind of give a reason why you change your second study. I feel like they did a good job explaining study 2 because for each modification they made to study 1, they also gave the heading for the section where they discussed the reasoning for this change. And this kind of goes into some human-computer interaction principles of, by doing this, it limited the amount of recall the reader needed to do and instead allowed recognition. So when you're processing information and you have to remember something, recall is more difficult because then you have to bring it up by yourself, whereas recognition jogs your memory essentially to give you a way of remembering what it is, which is pretty good. That's just kind of like a nice thing that I liked about it. And then another thing is that they kept comparing real world environments versus psychological tasks, and I really would have liked to seen a third study, maybe even, that showed the observations that they took from the second study and applied this to the real world environment to use that cross classification that they were talking about and check the accuracy of their classifiers. See if those same 22 classifiers were useful in the real world environment compared to the psychological task. I think there's more that could have been done with this, and I feel like it kind of just left off on a edge essentially of what else is there. So all in all, I think it was a good start into working memory load in realistic learning environments and the things that need to be considered to do so. In my second paper, Sound to Language, Different Cortical Processing for First and Second Languages in Elementary School Children, as revealed by a large-scale study using FNIRS. So this paper is a bit different. It's not directly brain-computer interaction, and I kind of get into why I'm discussing this in a little bit. But the goal and outcomes of the paper was that they wanted to identify what FNIRS data looks like when participants are presented with their native language, which in this case was Japanese, and it's going to be referred to L1 or language 1, and their secondary language, which in this case is English or L2/language 2. What they end up seeing is that there was a right to left hemisphere shift when lexical knowledge increases for both L1 and L2. So that means that as a person becomes more familiar in both their native and secondary language, the processing of it shifts from the right hemisphere to the left hemisphere, which isn't too surprising because the left hemisphere is where the regions for language processing are. Some notes is that this was a very large study. Instead of the previous one that had 10 participants, this study had 484 participants. The design was that children would listen to a Japanese or English word and then repeat it back. So if they heard like kokoro, then they would say kokoro. Or if they heard the word mammal, they would say the word mammal. So how they were judged on proficiency is that they would self-report the knowledge of the word. They had 3 options. It was, I'm familiar with this word is somewhat familiar, but I do not know it, and I have never heard this word, or roughly those 3 criteria. And then native speakers would judge the pronunciation, phoneme from phoneme, to see how well the child repeated it back. The most interesting thing that I personally found from this paper was that the L2, so the secondary language, processed as non-word auditory stimuli if the student did not know the word. And then some points brought up by the researchers is that they're unsure if the right hemispheric activity is due to either unfamiliarity with language 2, which would be the ideal outcome, or if it was the age of the participants, or if it was the task design. So what these last 2 mean is that would older participants, such as adults, have the same activation for L2 in the right hemisphere? Or the task design, would a non-phonological task still induce right hemispheric activity? So if something that's not auditory based, would it still be processed in the right hemisphere? Because at that point, everything's more left hemisphere oriented. So the reason why I discussed this study as well is because I feel like it would be a good application for expanding learning environments beyond just working memory load. So have a task or design for learning environment that revolves not only on someone's working memory load, so how immersed or difficult is the task for them, but also what is their proficiency in the subject to begin with. So language, I feel like, is something that isn't the most difficult because the regions for language processing are somewhat well defined of Broca and Wernicke's regions in the left hemisphere. And then we have more studies like Sugiura et al. That is showing the shift between different languages when you're learning a language. So if you could combine that with working memory load, how would that change a personalized learning environment to make it more efficient for someone who's learning material? And based off of that, my further thoughts or questions for you to think about for the discussion post is, why is it bad to use motor and perceptual confounds in BCI applications? What I mean by this is that if this helps classify the data and you know that these motor confounds are going to be present when someone's doing the real world task, why not use those as a way to classify the data? Like, why does it have to be this pure brain data? Why can't it also take in physiological measurements that show up in brain data? My next one is, what other fields could be combined with working memory load to improve learning environments? So like I said, language is one that's already predefined of the regions that it activates. Would we be able to do something like this with math? Would that activate certain regions as you get more proficient? You can see like a hemispherical shift. What are some pros and cons you think to using EEG and FNIRS in brain-computer interaction learning environments? So what are some good things for using EEG? What are some bad things? What are some good things for using FNIRS? What's some bad things? The most obvious one to me is the timing delay in FNIRS. It takes approximately 5 or 6 seconds for the FNIRS data to show up because of the delay of oxygen coming to the brain. Whereas EEG is instantaneous, so it's great if you want immediate feedback. And then what are some difficulties you foresee in using EEG and FNIRS regularly in classrooms? And I'd like you to think about the difficulties besides the cost. So like, let's say this equipment was readily available and cheap to access for everyone. What are some of the difficulties that you would see using EEG and FNIRS? Thank you for listening to my presentation. I hope everyone's staying safe and have a good day.